very warm welcome to all the viewers of this YouTube channel. My name is Atchuta Ramacharyulu and I am working as an assistant professor in the Department of Mechanical Engineering. Today, we are discussing a course named Elements of Mechanical Engineering, in which we are going to discuss anatomy of robot and joints. So the topic is all about robot and anatomy of robot. Now let us go into the topics. In the previous class, we have discussed about automation. In automation, there are three types. First one is fixed automation. Second one is programmable automation. Third one is flexible automation. So when we see all these automations, so fixed automation is a kind where we cannot change the program which is given to the machine or a control system. And then programmable automation is a system where we can change the program according to the need. And in flexible automation system, we can change the program and we can include more number of systems which are controlling different machines, and we can make very flexible designs. So because of that, the flexible automation system is very low in production rate compared to fixed and program. Coming to different automations, like in this slide, we have hard and soft automations. First of all, what is hard automation and what is soft automation? There is one difference between these two. Hard automation directly relates to the mechanical parts or elements which are being used in the control. When we are using some machines or computers, then we can call it as hard automation. When we are using some kind of program for automation, then we can call it as soft automation. Now let us see some of the basic differences between hard automation and soft automation. Now, cost effectiveness. First point is cost effectiveness. So in hard automation, this is very good at very high production value. Suppose I take the example of a thumbs up bottle company, where we produce a large number of thumbs up bottles, drink bottles, in a very small time. Because of this hard automation, the production rate is very high. Whatever the automation we will do in this manufacturing system, this is hard automation, because we don't need any program or a computer for that. We need a numerical control system which will manually operate the filling of the bottles and closing the caps and stickering the bottles. So all these things will be done by hard automation system. Coming to soft automation system, it has a moderate production volume, because here the soft automation is somewhat comparatively slow production rate because of the limitations of the system, because it does not use mechanical elements. It uses a software for automation. So this is soft automation, where we will have a medium production rate. And then flexibility. Coming to the flexibility, when we are using a machine for automation, like it comes under hard automation, it is not so flexible, because we can do limited operations in that machine. Coming to soft automation, like we take the example of a computer where we can write program. So in the soft automation, we can write different types of programs depending on the need. We can rewrite, and we can download the program, and we can modify the program, and we can take this program to some other place and we can use it. So the flexibility is more in soft automation because of the use of computer. And then life cycle. When we want to use the automated system for longer time, then this hard automation is very useful. In our hard automation, these systems can be used for longer periods. Okay, without changing any predefined program, we can use them continuously for like years. Comparatively, the soft automation is also have a longer period, but it is not long as the hard automation, because there may occur some software crash or something. In both cases, crashes and failures are uh, redundant. They can happen, but compared to hard automation, the soft automation is it works for a very short period when compared to hard automation. And then batch production. When we want to manufacture a mechanical element using this hard automation, so the batch production is not suitable here. We can produce some n number of things continuously in hard automation, so that it is not suitable for batch production. So we cannot stop and start the things. And again, in soft automation, this is very suitable for batch production, because we can manufacture a product, then we can stop the system, we can change the code, and we can use the system for next another type of production. And then control through software. So in hard automation, controlling the automation through software is not possible, because we have to use some hardware units, and we are using some machines which are controlled by numerical machines. So control through software is not possible, and it is no need here in soft or hard automation. Whereas in soft automation, we'll use some softwares for designing, for the coding. So we will definitely use softwares for controlling the soft automation. And then efficiency of the operation. When we compare the efficiency of operations between soft and hard automations, the efficiency in hard automation is very high. And similarly, in soft automation, it is equally high, because we know softwares are very fast and accurate nowadays. If I have a machine which is operated by a human being and a equally software, so then when we compare the efficiency of the systems, okay, both are automated systems. Now this hard automated system will have very high efficiency. The soft automated system will have equal efficiency compared to hard automation. So in the perspective of efficiency, both the automations are very similar. Both systems will have same efficiency. Now we'll see some examples of hard automation and soft automation. So automatic machines, machine not controlled through softwares, and transfer lines. So these are some of the examples of hard automation. So here automation is there, but we don't use computer or a software for controlling the system. So soft automation, some examples are CNC machines, robots, reprogrammable machines. So these are the examples of soft automated systems. We will use soft automation for CNC machines, because we are studying the automated systems related to computer numerical control and robots. So we will use the robots, CNC machines, which are directly related to soft automation, because we will use the software for controlling them. Now we'll go to the next topic. So this is the actual topic of this class, anatomy of a robot. Now, in the previous lecture, we have seen what is a robot, and we have seen what are the different parts of a robot. What is the history of a robot? How robots was developed? How robots were very frequent in back in the years, where they were used in films. The word, how the robot word has been used for the first time back in the year 1960s. And we have seen in which year the Unimation was formed back in the year 1962, where the first industrial robots were developed. So we are studying the CNC systems. We will discuss the industrial robots only. Industrial robots. So as you can see in this picture, any industrial robot will be like this. It will have some parts. Now we'll see what are those parts in detail. Any industrial robot will have a ground. on which the base of the robot is fixed. Now this part is fixed on the ground. Okay, so this is the base part which does not move, it is static. And then on this we will have a link. So this is link 0. Link 0 is there, where this link is directly attached to the base and it will carry the whole entire length of the robot. Okay, so this link is also mostly it is stable, it does not move with respect to the base. This is also static with the base. Now see here, there is a joint. I am naming this as joint 1. Now this joint is where we connect these two links. This is link 0 and this is link 1. These two links are connected by a joint. See, this is the kind of terminology we are going to use in robots, links and joints. So it is very important to know which part of the robot is called as link and which part of the robot is called as joint. Now here we can see these two links, link 0 and link 1 are connected by a joint which we named it as joint 1. And then we have a second link, link 2. Link 2 is here and link 1. Link 1 and link 2 are connected by another joint, and this joint we named it as joint 2. And this part at the end of the link 2 we have is the end of arm. This is where we will connect different tools or any manipulators. Okay, so at the end point of the robot, what we call it as end effector. We will call it as end effector. So there are many devices which can be fixed to this end of the robot. They are like two types. First one is an actuator or gripper. And second one is tool. So at the end of the robot, at the end of the arm of the robot, we can connect two kind of devices. First one is actuator or gripper. So we will discuss about actuator and gripper in the coming classes. Gripper is nothing but a tool which can hold objects. Simply it is like a human hand. And actuator is nothing but it can create some movement, linear or rotational movement. And in second kind of objects we can fix to the end of the arm is tool. We can attach many kinds of tools like welding torch, machining tools, drilling tools, like different types of tools we can attach to the robotic end, where we call it as end effector. Okay. Now, so this is all about the anatomy of the robot. Anatomy means we will see what are the different parts of the robot. Now we have, this is a robot which has 3 links and 2 joints. So this robot can move in about 2 degrees of freedom. Now here the number of joints are 2. So that is why the degrees of freedom of this robot is 2. We will see what is degrees of freedom in the next coming slides. So the degree of freedom of this robot is 2. So degree of freedom we will see. So this is all about the anatomy of the robot. Now we will go to the next slide. Now we will see what is the degree of freedom. So in this slide we can see a robot is there. This is what we call it as industrial robot. And this has like many joints are there, many links are there. We will discuss one by one all these links, where the motion is possible, in which direction the motion happens, all these things we can study here. So there are like 6 axes are there. So the degree of freedom of this robot is 6. Okay. Now we will see the basic definition of degrees of freedom. So degree of freedom is nothing but the individual joint motion associated with the performance of a task. Okay. When we have links and joints in the robot, these links can move in some direction. So depending on the motion that is possible for each link, so the degree of freedom is calculated. So in this definition we can see individual motion associated with the performance of a task. Individual motion of each link is calculated as 1 degree of freedom. Now, the opening and closing of the gripper is not considered as degrees of freedom. We'll see what is a gripper. Gripper is a mechanical element which is connected to the end point of the robot, like we will connect that here. So the gripper will be like this. So the gripper is used to hold an object. It can move in, like it can hold the object. Here the object will be there. It can hold the object. Now for holding, it can move in this direction, towards and outwards. So this motion is not considered as degrees of freedom. So this is an important point while we are calculating the degrees of freedom. Okay. So the opening and closing of the gripper is not considered as degrees of freedom. Now here in this diagram we can see there is a robot which has many links and joints. We'll see how many degrees of freedom, in how many free directions this robot can move. Okay. First one is here. First axis is there. We can see here, this is the actual diagram of the robot where we can see the base. This is the base. This point is called base. This is fixed and it cannot move. Okay, on this base, there is a wheel attached here. Now here we can see where the movement happens. It can rotate about this axis. It can rotate about horizontal plane. Okay, so this is first axis of rotation. So here we have 1 degrees of freedom. And then here we can see there is a second axis. Now, how this second axis will rotate? This second axis will rotate about this vertical plane. This can rotate in this direction. Okay, it can rotate about this point. So if there is an axis here, it can rotate about a vertical plane. Okay, so this is second axis. Now we have 2 degrees of freedom. And again, we can see the third one is somewhere here. Now the third movement is here. Here there is a axis here. And about this axis, there will be rotation. Okay, now these two are also rotations only. First degrees of freedom is also rotation. Second one is also rotation. We'll see how many rotations are possible. And again here at the third axis, this is where we have rotation again. Okay, 3 rotations are there. This will rotate about a plane which is perpendicular to the horizontal plane. Okay, and again here another axis is there. See here, another axis is there. This is axis 4. So the axis 4 will rotate about this direction. It can rotate in the circular motion about, this is the axis of the robot. Okay, now we have 4th rotation. And again we can see at the 5th point. So at the 5th axis, we have a rotation. I think this is the point where the robot can rotate. This can rotate in this direction. Okay, at this point we have 5th axis. So 5 rotations are possible so far. And again here at the end effector, end point where we will connect the end effector, here the 6th axis is there where it will rotate in this direction, like it can rotate clockwise or anti-clockwise. Okay, at this point. Okay, now total there are 6 free rotations this robot can move. So the degrees of freedom of this robot is 6. Okay, the degrees of freedom of this robot is 6. So depending on in how many free rotations the robot can move, so the degrees of freedom value can be calculated. Okay, so this is all about the degrees of freedom. It is the number of axes in which a robot can move freely in order to make some actions or perform a task. There are many tasks that can be performed by any robot, like pick and place operations or operations related to machining. Okay, machining operations like drilling, welding, etc. Now we'll go to the next slide. We'll see what are the robot specifications. Every robot will have some specifications like these things. They have 7 kind of specifications here. So depending on the specification, we can select a robot for our particular purpose. If I want to use the robot for a pick and place operation, and it also depends on the dimensions up to which a robot should reach. So depending on that, I can select a robot based on these specifications. Okay. Now we'll see what are the specifications. First one is number of axes. How many axes are there? Okay. Now in the previous slide, just now we have seen there are 6 axes are there. In this slide, there are 6 axes. So the degrees of freedom of this robot is 6. Okay. Similarly, depending on the number of axes a robot has, that can be taken into consideration while selecting a robot. Now, in this table, we are seeing the dimensions also. The number of axes does not have any dimensions. It is a simple number. And then capacity. How much force or how much weight a robot can lift, that is also taken as capacity of the robot. This is also considered while selecting a robot. So the units for capacity are kg force. Okay. And then third one is speed. We know the robots are moving. Robots will move at different joints using their links. So the speed of the robot is also very important. The speed of each individual link is calculated, and each individual motion of the link is considered and calculated as speed of the robot. Now, the units for speed of the robot is millimeters per second. So, in how many millimeters it is moving per second can be calculated, and it is taken as a specification for the robot. And the next specification is reach and stroke. So, reach and stroke are directly related to how much distance or how much volume around the robot it can reach. So, I'm going to the previous slide where here see this is a robot. It will have some volume around the robot where it can reach. Beyond that limit, it cannot go and work because the robots are fixed to the base. Okay, robots can move in a volume created around them. So if I have a volume around this robot, the volume is fixed for the robot, and this is called, this entire volume where the robot can freely work and it can reach is called a robot work envelope. Okay, work envelope. So the volume around the robot is called work envelope where it can reach. Beyond that point, the robot cannot work. And even sometimes there are some blind spots where the robot cannot reach inside the work envelope. Okay, there are some, generally these are all mechanical elements. They have some constraints and they have some what we call boundary conditions will be there. That is where these robot cannot reach a certain point. If I place an object near this joint, the robotic arm may not reach there because the links are too long. It cannot reach this point. So, work envelope can be calculated by measuring the entire volume minus the black spots or dark spot where the robot cannot reach. So, that should be subtracted from the work envelopes. So, that is where we will get the work envelope volume. Okay. So, here reach and stroke. So, how much distance the robot can reach and how much stroke it can do works. So, they are all also taken as specification and it is measured in millimeters. Okay. So, this is generally reach and stroke are calculated in linear distance. And then fifth one is operating environment. Like some robots are designed to work in hot temperature. Some robots are designed to work in cold temperature. And some robots are designed to work in at a very a environment where there is lot amount of moisture. So depending on the different environmental condition, okay, we can choose different robots. Sometimes robots are being used for painting the car body. Then the robots are covered with some kind of covers so that the robot does not get any damage because of the paints that is being sprayed on the car body. So depending on the different environment, we will use different robots. Next one is tool orientation. So tool orientation is nothing but in which angle the tool can rotate. Okay, this is calculated in degrees or radians. This is the rotation of the tool about which it can rotate. Okay, and performance parameters. Performance parameters are some parameters which are calculated for the robot about which the robot can work. Okay, so these are calculated in millimeters. So these are some of the robot specifications where we can select a robot for a particular purpose. Now we'll go to the next slide. Here we have degrees of freedom again. So the degrees of freedom is any robot will have the degrees of freedom, and we have seen in the previous slide. Now what we are going to study here is in how many free movements are possible for a robot. Okay, so we can take the examples of translation and rotation. There are two kinds of motions possible for any robot. So these are the possible motions of any robotic link or joint. So in translation, there are so here we have a diagram of a ship where we can study the motions. Like different motions can be studied here when the ship is going in the water. So there are different motions possible for the ship. Now we can compare the different motions of this ship with the robot. Okay. Now here we can see there are two different types of motions: translation and rotation. First one is moving up and down. Moving up and down, like in this direction, up and down. So this motion is called as heaving. And second one is moving left and right. Now in this direction, left and right. Okay. Now moving this left and right is called as swaying. And third one is moving forward and backward. Moving forward and backward. So all these are translatory motions. We don't have any rotation. They are simply linear motion. Okay. So moving forward and backward is called as surging. This is also used in the word surging is also used in electrical related terminology, where it is used for electrical surges. Okay. Now the surging is a movement where forward and backward movement will be there. So these are three different types of translatory motions which are possible in ships as well as in robots also. That is why we are discussing. And we can see in rotation there are three different motions. One is pitching. Pitching means tilting forward and backward. In this diagram we can see these are not linear motions. These are all rotatory motions. Okay, they will have some angle. So pitching is nothing but moving forward and backward. Like moving forward and backward. So that is called pitching. And then swivels left and right. So swiveling left and right means moving to the side. Swiveling left and right. Like yawing means you can see it can move in this direction. Like if I have an object like this, my hand is a ship. So swiveling means it will move like this. Okay, moving to the left and right sides. Okay, this is one movement. And then pivots side by side. So this is called rolling. Rolling is nothing but pivoting. Like it can move in the horizontal plane. Okay, this is pivoting. I mean, this is rolling. Okay, so we'll see all the three motions of the ship. First one is tilting forward and backward, which is pitching. This is pitching. Second one is yawing. Yawing means rolling about the horizontal plane. Okay, this is yawing, and pivots to the side, rolling. Okay, these are the three different motions possible for any ship because they are ships are working in water. Mostly they can see all these three motions. Now these three motions, along with the translatory motions, all these motions are possible for robots also. Now whenever a robot is moving in any of these style, we can call them with the names: heaving, swaying, surging, and pitching, yawing, and rolling. So these are the different motions that are possible for any robot. We'll go to the next slide. Now you can see different joints in robots. What are the different joints in robot? So there are different types of joints which are being used in robots for creating motion. Okay. The ultimate use of any joint is to use them for motion, creating motion. They might be linear motion or rotational motion. As we have seen in the previous slide, we have translatory motions and we have rotational motions. Here, the first link is linear. Linear joint is there. So, in this joint, we have an input link and an output link. Simply, we can see in this part, the joint is made where we can see linear motion. Okay, here we can see it is written here, linear motion is there, to and fro motion, outwards and inwards. Okay, so here the input link is stable, the output link can be moved in and out by using any kind of actuator. We have seen what is an actuator. It can create linear or rotational motions. So what kind of actuator can we use here? We can use hydraulic or pneumatic piston cylinder arrangement for creating this linear movement. Okay, this is where the linear joint is used. Okay, now we can see the second type, orthogonal joint. So orthogonal joint is also very similar to the linear joint, but here the axis of movement, that means in which we are using, is perpendicular to the initial link. See here, input link is there, output link is there. These two are perpendicular to each other. In the first, to the linear joint, these two are parallel. The input link and output link are parallel to each other. Here the input link and output link are perpendicular to each other, where the output link will be sliding to the left or right on the input link. Okay, so this is what we call it as orthogonal joint. For creating this motion also, we will use hydraulic or pneumatic piston cylinder arrangement. Now we have a third kind of joint, which is rotational joint, where we will have an input link, and on this an output link will be connected, and it can rotate in this direction, and it can rotate about a plane perpendicular to the input link. Okay, so here rotation is possible. The output link can rotate. So for creating the rotational motion, we will use a actuator which is like electric motor or a stepper motor. So we will use these kind of actuators for creating this motion. And then fourth one is twisting joint. So see here the input link is there, it is on which an output link is connected, like it is connected as a screw and bolt arrangement. Okay, now this output link can rotate in the perpendicular plane. Okay, it can rotate on the plane, it can move forward or backward, it can move in this direction also. Okay, just only moving on this plane is not useful, even though it is also used like for some operations. Okay, now so this can rotate and it can move forward and backward also. Now see here, revolving joint, the last kind of joint where in robots is revolving joint, where the input link and output link are perpendicular to each other, and they are connected with the help of a swivel. So this connection or joint will make the output link rotate about the axis of the input link. Okay, it can rotate like this. It can rotate about the axis of the input link. Okay, these are the different joints used in robots: linear joint, orthogonal joint, rotational joint, twisting joint, and the revolving joint. These are the 5 kinds of joints used in robotics. Now we'll see what is a robot configuration. What are the different types of robot configurations available in the market for any robot? See here, first of all, we should know what is configuration. Configuration is nothing but in which kind of motion the robots are moving, or which kind of path the robots are designed to move. Okay, so there are different movements will be possible for any robot, because we have seen there are a lot of degrees of freedom can be created. We can go to the previous slide and see here there are 1, 2, 3 and another 3 motions are there. So all these 6 motions can be mixed and combined, and they can be combined in such a way, we can create many number of motions. Okay, permutations and combinations we can calculate with that. We can have n number of possibilities of creating different motions. Okay, now in this slide we can see different configurations of the robots. See, first one is Cartesian robot. So the Cartesian robot will have three motions. Three motions are possible for this Cartesian robot. So which indicates the degrees of freedom is 3. So in how many directions this robot can move, or the links in the robot can move are, so first one is horizontal direction. This link can move in this direction, in the horizontal direction. And again, this link, it can move up and down about this vertical rod. Okay, now this link can move up and down. And again, in this link, another small link is there. This link can move in this direction. Okay, so overall it can move. It has three axes which are perpendicular to each other. Now this axis is 1, this is 2, and this is 3. So all these three axes are perpendicular to each other, which makes, or which allows this robotic arm to move in three different motions. Okay, 3 degrees of freedom is possible for this motion. We can observe all the motions are linear here. All are linear. So there is no rotation here in any joint. So all the motions are linear. Horizontal motion, up and down motion, to and fro motion. All 3 motions are linear only. Now second kind of configuration is cylindrical robot. In cylindrical robot, there are 2 linear motions and 1 rotational motion is possible. Okay, I will write here. So this is 3L robot. This is 2LR robot. So 2 linear motions are possible and 1 rotation is possible in this robot. Now see, this is the base of the robot, where it does not move anywhere. On this we have a vertical cylindrical column on which the entire system can move. Okay, here the entire robotic system can move, or it can rotate about this vertical axis. Okay, we have a vertical axis here. The robot can rotate about this vertical axis. Now another motion is it can go up and down. Now this link is there. Now this link can move up or down depending on the requirement. This is another degree of freedom, which is second linear motion. And again, another link is there in this second link. The third link is attached inside. This link can go inside or outside. So overall, there are 2 linear motions and 1 rotary motion is possible. And see here, polar or spheric robot. Here we can see 2 rotational motions and 1 linear motion is possible. Okay. We can see here the entire robot system can rotate about this axis. There is an axis, vertical axis. Okay. And again, this link can rotate about this axis. Here another axis should be there. This is another axis where it can rotate about that axis. Okay. This link can rotate. So second rotation. And third rotation is moving in and out. The third link can go inside or outside. So this is third motion. So 2 rotational motions and 1 linear motion is possible in polar or spheric robots. Okay. Now I will write the different combinations. The first one is 3 linear motions. Second one is 2 linear and 1 rotation. Third one is 1 linear and 2 rotations. So this is how we should remember all these configurations. And the fourth one is SCARA robot. SCARA robot is where we will have 2 rotations and 1 linear motion. Okay. See here, we have 2 rotations which are in the same plane. They can rotate in the same plane, but they have axes which are offset from each other. So these 2 are the axes about which rotation is possible, but these 2 axes are very far from each other. So this is where SCARA robots are used. So this kind of arrangement is called as a SCARA. So here, third moment is linear, which is the tool can move up and down. Okay, this movement is linear. So here we have one linear and two rotational motions. See here, in polar and spheric robots, both have same kind of configuration. Okay, here in polar or spheric robot, the two rotational uh, the two rotational axes are perpendicular to each other. So this is one axis and this is another axis. So the two rotational axes are perpendicular to each other. Coming to SCARA robot, the two rotational axes are parallel to each other. Okay, when the two axes are parallel to each other, that is called as SCARA robot. When they are perpendicular to each other, that can be called as a polar or spheric robot. And then last kind of configuration we are going to see today is angular or anthropomorphic robot. So this is where we are going to see three motions. Three rotational motions are there. There is no linear motion here. So all the three, out of these three, two are parallel to each other. These two are parallel. The axis of these two rotations are parallel. And the third one is perpendicular to this two. Okay. We have three rotations here. Okay. So this is called as angular or anthropomorphic robot. Okay. Now we have seen total 5 kinds of robot configurations. So out of these 5 kinds of robotic configurations, we have seen 3 linear for Cartesian robots, 2 linear and 1 rotation for cylindrical robot, and polar or spheric robot will have 1 linear and 2 rotationals, and SCARA robot will have 1 linear and 2 rotations, which are similar to polar, but the axis of rotations are different for these two robots. And angular robot will have 3 rotations. There is no linear motion possible in this kind of robots. So all these different types of robots can be used depending on the purpose, depending on the process in which we are using the robots. So now we'll see what is a robotic wrist. See, in this picture we can see there is a robotic wrist. So what does this robotic wrist will do? So this wrist is attached to the end of the arm. We have seen previously that there are many links in the robots, out of which one link will be end point of the robot. So that is where we will connect this arm, or we will connect this wrist to that arm, where it can have 3 different motions. As we have seen in the previous slide, there are 3 rotational motions are possible for this. Okay, for this wrist. So wrist assembly is attached to the end of arm. End effectors are attached to wrist assembly. Okay. Now this is the attachment given to the last link of the arm. Okay. Suppose I have a robot like this. Now for this point, I have joint 1 and joint 2. At joint 2 or link 2, this is link 1 and link 2. I will connect this wrist to the link 2. Okay. To this wrist, I will connect the end effector. End effectors are like grippers or tools. Now this end effector, the robot wrist is where it will have 3 kind of motions. One is rotation about this axis. It can rotate about this axis. Second motion is yaw motion. It can rotate about this axis, horizontal plane. And third one is pitching. It can rotate about this axis. So it can go up or down. Up and down, rotation about vertical axis, and rolling. So these are the 3 motions possible for this wrist. So this is very useful in many robots, where to this robotic wrist we can connect the end effector. Okay. Now function of wrist assembly is to orient the end effector. The main function of this as a wrist is to orient the end effector. It can change the directions of the end effector. Okay, it can move up and down, left and right, and it can roll. Okay, and it has 3 degrees of freedom. As we can see, there are 3 motions possible here. The degrees of freedom of this robotic wrist is 3. Okay, degree of freedom is 3. So that's all for today. And so far we have discussed robot anatomy, soft and hard automations, what is degrees of freedom, what are the different joints used in robots, what are the different configurations used in robots, and what is a robotic wrist. We have seen all these topics. In the coming class, or we can see what are the different actuators, or what are the different parts of a robot. Okay, we have seen already what are the different parts. We will see in detail what are the different actuators or different tools can be connected to the robotic end effector. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.